This is lesson 4.2, Algebra 2. It's on inverses of relations and functions. And I'm going to save this joke for later because it's not going to make any sense at all if I do it now. So we'll just have to wait on that one. And we'll start off by making some definitions here. The first one is relation. Oops. A relation is a set of ordered pairs. So anytime you make a t-chart when you're going to graph a function, you're making a t-chart of a relation. So a function is also a relation because it's a set of ordered pairs, but a function happens to be a specific type of relation. So all functions are relations, but not all relations are functions. And a function, I believe we've defined it before, but it's a very important definition, so I am going to define it again. It is a relation, but it's a rule that assigns each x in the domain to exactly one y in the range. Okay. And we've been working with functions all semester, so you have a good feel of some examples like quadratic functions, cubic functions, linear functions. And yesterday, the exponential growth and decay functions. Well, there's also an inverse function. And inverse functions undo each other. So, for instance, one of my favorite ones is x squared. If we want to undo x squared, so if f of x is x squared, we would undo x squared by taking the square root. So the inverse of x squared is the square root of x. And the way we write the inverse is we write, since it's the inverse of f, we start with f, but we write f to the negative 1 of x. And that means the inverse of f. It doesn't mean f to the negative 1. I mean, it's not like you're raising it to the negative 1. It's just a notation. So when you see that, you'll just understand that that means inverse. And then, was that all? Okay, so we've covered what I wanted to cover on this screen. The notation, the inverse function notation, is this last part that I just wrote down. And here in example 1, we have a relation because we have a set of ordered pairs in this table. And we're going to graph this relation, and then we're going to connect the points. So looking at this, it looks like I need to go up to 7 and 8. So I'm going to be, all these are in the first quadrant. So I'm going to draw my axes accordingly. Whoops. And I'm just going to count by ones. You won't have graph paper unless you happen to have some, but that's okay. So my first ordered pair is the point 0, 2. So we're going to plot that, and then the point 1, 4, 2, 5, 4, 6, and 8, 7. Oops, 8, 7. Okay, and it says to connect the points, and it's obviously not linear, so I'm going to connect it with a smooth curve, like so. And it says identify the domain and range. Oh, before we do that though, we need to graph the inverse. And I was trying to decide if the book is thinking of these as discrete points, but they do say to connect them. So I'm going to assume, and I'm trying to figure out if the book is thinking that we have endpoints or does it continue on forever. Let me take a quick glance just so I can see what their intention is here, because it will depend. It'll affect how we answer this. Okay, so the book is going to consider these as endpoints. So when we do our domain and range, those are stopping points. It does not go on forever here. And unfortunately, the book is not very clear about that, so it's hard to tell. I had to look to see what they were thinking. And it wasn't written in the problem, so I didn't know. So here's our relation, and we are connecting them, so we are including the points that are along that whole curve, not just these discrete points. The discrete points are just the points that are in the table. Okay, so now we're back on track. Okay, so I'm going to call that, just so I have some notation, we'll just call it y. That works. And then it says graph the inverse. Well, in order to graph the inverse, what we are going to do is we are going to swap the x and the y. So with an inverse, we swap the x and y to get the inverse function, or relation in this case. Actually, it would be a function as well, because every x that's in this table is paired with exactly one y. 8 is just paired with 1, that's 7, and so on. So this would be, and if you wanted to make the inverse, you would do x, and I'm going to call this y inverse, y to the negative 1, that means y inverse. And now, let's see, 1, 2, 3, 4, we have 5 points. All of the y's are going to become the x's. And all of the x's are going to become the y's, because we switched the x and the y. And then I'm going to graph those new points, and that's going to be my inverse. So I'm going to go to a different color. The point 2, 0 is here. The point 4, 1. The point 5, 2. 6, 4. And 7, 8. Over 7, up 8. And then we're going to connect that with a smooth curve, and we do have endpoints, so we will start and stop at the ends. And that's going to be y inverse. And that looks pretty cool. That's symmetrical, isn't it? And what is the line of symmetry? What are those two graphs symmetrical about? Well, you can think and guess. You can maybe guess. If you guessed y equals x, you would be correct. So the original relation, or the original function in this case, and its inverse are reflections over the line y equals x. The line y equals x it would go through 1, 1, 2, 2, and so on. There's the line y equals x. So let's write this down. This is important. A graph, or I should have said a relation. Oh well. I think that would be better. A relation and its inverse are reflections over the line y equals x. That's always true. And then in the original problem it says identify the domain and the range of each relation. So what I'll do, we're done with the y equals x right now. So let's see, I'm going to make a little table. Here's y inverse. How about the domain of y can go here, and then the range can go here. So if we look at y, which was the blue one, and its domain, what I'd like you to do, ideally, is to fill this out yourself. Pause the tape, fill it out, and then come back. So I'm going to please ask you to do that, and then I will supply the answers. Okay, so now hopefully you've done this, and you should see that the domain of y, that was the blue one, those are the x's. They start at 0, and I'll use the same notation. Well, I kind of like interval notation. Let's use interval notation. Why not? It's actually a little easier. So it starts at 0, and that's an endpoint. It's closed. And it goes up to 8 is the highest x value. And then on the range, the least y value, the lowest y value on the blue curve is 2. And the highest y value on the blue curve is 7. For the inverse, which is the orange one, the smallest x value, that's on the domain, is 2. And the largest x value is 7. And then the range, which would be the smallest y value of the orange curve, the smallest y value is 0. And the largest y value is 8. Do you see anything interesting in that table? Well, if you notice that the domain and ranges of a function and its inverse are swapped, then you are absolutely correct. Just because the x's and the y's swap, well then the domain and the range also swaps. So those are some key things to know about inverses. And then here the book has mentioned the additive inverse of 3 is -3. They're just seeing, where have you seen that word inverse before? It's kind of like 2. If you added 3, you would undo it by subtracting 3. The multiplicative inverse of 5 is 1/5. So if you multiplied by 5, you would undo it by dividing by 5 or by multiplying by the reciprocal 1/5. Inverses undo. Okay, now on this one, ideally I would like you to try this on your own. Pause the tape, and then when you resume, I will be doing it. And now I will be doing it. So we're going to graph this relation. This time it's already marked on the graph for us. So x, okay, we've got the point 1, 0. And 3, 1. 4, 2. 5, 3. And 6, 5. Again, we'll consider these to be the endpoints at the ends there, and we'll connect them with a smooth curve just like we did. Let's call that y. Change colors. These do not change color well. That's too similar. Let's do this tan color. Sorry. And then to do the inverse, we need to swap the x and the y. Okay, so all of the y's become x's. 0, 1, 2, 3, 5. And all the x's become y's. So I'm simply switching them. And then we're going to go ahead and graph those points. So 0, 1. Sorry, this is a little bit light, but I think these colors go well together. Over 1, up 3. Over 2, up 4. Sorry. I always seem to have kind of a stuffed up system here. 3 and 3, 5. Okay. And then 5, 6. And that will get, whoa, not so great. There's your y inverse. Double check, and does it look like it's reflected over the line y equals x? So that y equals x goes through, 2, 2, 3, 3, 4, 4, and so on. Whoops, I'm not doing so hot. So y equals x. Yes, indeed, the inverse and the original function are reflections of each other. So we've graphed the relation, we've graphed the inverse, now we need to identify the domain and the range of each one. So for that, I'm going to do a chart again. Y inverse, domain, range, domain, and again, do these on, hopefully you've done this all on your own. The domain are the x's for the y. I like to look at graphs. I could look at the table, but I like graphs. Let's see, y is the magenta curve, and the domain, the x's go from 1 to 6. And on that same magenta curve, the y's go from 0 to 5. With the endpoints included, therefore the square brackets. Y inverse, the domain, that's the x's, they go from 0 to 5. And the range or the y's, they go from 1 to 6. And then check your table here and make sure the domain and the range is swapped. And indeed they did, so I know that I've done this correctly. So when the relation is also a function, which actually has been the case so far on these examples we've worked, you can write the inverse of the function as f to the -1 of x. So we've talked about that already. And that does not indicate a reciprocal at all. It's just simply notation. which means it's a way of writing it. We already talked about the fact that inverse functions undo each other. And then the example the book is using here in this original function, x is you're adding 6 to x. So if you were to undo addition, you would subtract. So the inverse is going to be the undoing. What undoes addition in this case? Subtraction. And here too, if you put in 3, the input is 3. So you're putting in 3 for x. 3 plus 6, you're getting an output of 9. Then if you take your output and put it into the inverse, so if you put 9 in here, 9 minus 6, you'll get the output of 3, which was the original input. So it's a cycle, like a loop. That's how you can check your work when you're finding inverses. It says to find the inverse function, use the inverse operation. And that's true. Now they're going to give us some really easy ones that we can do in our head. I'm also going to show you a standard way that will always work. If you like formulas and algebra, you might like this way better. I tend to, so I like to do it this way that I'm going to also show you. I'll show you the simple way, just thinking about it, and then I'll show you the more algebraic way. So the simple way, which is what the intention of the book is, it says use inverse operations to write the inverse of f of x equals 2x. Well, the 2 is being multiplied to the x, so to undo multiplication, you would divide. So f inverse would be x divided by 2. The other way to do this is, it's a little bit of a process, switch the x and y and solve for the new y, and that will give you the inverse. So this is another way to find an inverse function. This way will work every time. I prefer, I don't know, my brain seems to work that way. So I'll show you what I'm talking about. So originally, the f of x is y. So originally you have y equals 2x. So inverses, we swap the x and the y. So I'm going to go ahead and swap the x and the y. So the y will become x, and the x will become y. So we will get this equation. And then we're going to solve for the new y. So if I want to solve for y, I'll divide by 2. So y will equal x over 2. And the y is now, this is the inverse, so we label it as y to the negative 1. Or actually, in this case, I should probably write it as f of x to the negative 1. And the way you can check this is, I'll just check it here. So it says use the input x equals 7 in f of x. Okay, so f of x, so we're going to put in 7 there. So that's going to be 2 times 7, which is 14. Then we're going to take the 14 and plug it into the inverse. So f inverse of 14 would be 14 divided by 2, which is 7. And that brings you back to where you started. If that happens, that means you've done it correctly. Right? So please do these on your own, and then check the tape, and I will be doing them for you as well. So the fast way, the simple way is, this is x divided by 3, so the inverse rather would be 3 times x. The other way to do it is start with y equals x over 3, switch the x and the y, and solve for y by multiplying by 3. So you take your pick on how you want to do it. Oh, and this would be y inverse, by the way. So I'm done. I did it. I found the inverse. Okay, on this other one, you undo addition by subtracting. So f inverse would be x minus 2/3. The other way, swap the x and the y. So originally f of x was the y, so it's now going to be the x. X now becomes y, because this was originally y. So I swap the x and the y, and I solve for the new y. So I'm going to be subtracting 2/3 from both sides. So I'm going to get x minus 2/3 equals y, which in this case is f inverse. So I'm getting the same result. I mean, obviously, the simple way is much faster. But sometimes when you get into the harder ones, the other way is going to be very good too, because it'll always work, especially if you're not sure which one, what the inverse is. So this one's a little more complicated. It has two parts. I mean, there's a dividing by 4 and there's a subtracting of 5. You can use inverse operations, which is the simple way, by undoing. And you undo by adding first. So we'll do it the simple way first. So originally, I mean, really the simple way and the way I'm, the switching the x and y are really basically the same thing. So you're going to undo this. You know what? Scrap that. I'm just going to switch the x and y because it's really the same thing and I don't want to waste your time. So let's do it the way where you switch the x and the y. So this is originally the y. I'm going to make it an x. I'm going to make the x a y. And then we're going to solve for the new y. So you're going to add 5 to both sides. And you're going to multiply both sides by 4. Make sure you multiply the whole thing by 4. And you can leave it like that, or you can distribute it if you want. And then this y is actually f inverse. It says you check by using a sample input. Okay, let's do something easy. How about 4? Because if I did 4 divided by 4, I would get a whole number there. So let's do f of 4. This is our check. Plugging 4 in, I'm going to have 4 over 4 minus 5. So that's 1 minus 5 is negative 4. Now I'm going to take that negative 4 and put it into my inverse. So I'm going to find f inverse of negative 4. So that's going to be 4 times negative 4 plus 20. I'm putting in the negative 4 down here, in here for x, in my f inverse. That's going to be negative 16 plus 20, which is 4, which is back to what we started with. So I just randomly chose 4. I chose it because it was easy to evaluate. 4 divided by 4 is 1. I didn't want fractions. Okay, we better move along. Same deal. So do this on your own, and then I'll be doing it for you. Okay, I'm going to do it what I consider the fast way is to swap the x and the y. So this is originally y. I'm going to make it x, change the x to a y. Solve for the new y. I'm going to be adding 7 to both sides. Solve for y. That's going to be division by 5 on both sides. And that's actually my inverse. So label it y inverse. All right. And then let's do a quick check. A QC, that's quick check. It doesn't really matter what I'm going to choose. Let's just find f of, I don't know, let's just use something easy, f of 1. So that's going to be 5 times 1 minus 7. That's 5 minus 7 is negative 2. Now I'm going to take the negative 2, plug it into f inverse. This is f inverse. F inverse of negative 2. So I'm going to have negative 2 plus 7 over 5. And this is good news because I can see that that's going to be 5 over 5, which is 1, which is back to with what we started with. Checks are kind of fun on this one. Okay, on this one they want us to graph f and then find the inverse like we've been doing and then graph that. And what should the graphs be doing? Reflections of each other across the line y equals x. So I'm going to graph this. It's already in slope-intercept form. Sorry I switched to boring black. Colors are much more interesting. So I'll switch here for you. I like magenta. It's pretty. Okay, we've got it in slope-intercept form. So this is the intercept, the y-intercept. This is the slope. Hopefully you remember that. The y-intercept is 6. 1, 2, 3, 4, 5, 6. And then we're going to rise 3 and run 1, because this is over 1. Okay, up 3 over 1. I can also go down 3 and left 1. Down 1, 2, 3, and left 1 again. And that's a good idea to do that. It's nice to know the x-intercepts and the y-intercepts. X and y-intercepts. That's f of x. Then the easiest way, in my opinion, to find the f inverse is to switch the x and y. So this becomes x. The x becomes y. Solve for the new y. So we have to subtract 6 first from both sides. and divide by 3. So x minus 6 over 3 will be f inverse. Let's graph that. Well, that one, I don't want to graph it like it's written, so I'm going to break it into, two parts. So the x over 3 minus the 6 over 3 is how we do that. That's an equal sign. Which is the same as y inverse, I'll say, is x over 3 minus 2. So go down 2. That's my y-intercept. And this time I have a slope. Do you see the slope in there? There's a 1 in front of the x, so the slope is 1/3. I'm going to rise 1 and run 1, 2, 3. Rise another 1 and I'll run 3 more. I can also go down 1 and left. 1, 2, 3. Whoa. That blue one there is my inverse, f inverse. Okay, just for fun, let's do a check and let's graph y equals x. It's going to go 1, 1, 2, 2, 3, 3, -1, -1, and so on. Whoa, I'm not doing so hot today. Y equals x. Do they look symmetrical about that line? Indeed they do. That's a pretty nice indication. So we've graphed it, we've written and graphed the inverse. Here's the inverse, and the graphs are up there. And then down here, the book is finally telling you how I've been doing it all along. Great. So please do this one on your own, and then you can check the tape for the solution. Whoa. Okay, I need a graph. I say tape because I'm from old school. You'll have to forgive me. Okay, so I'm graphing. Let's get some color here. Oops, it sure doesn't like to switch. Okay, so on this one, my y-intercept is 2. My slope is 2/3, so rise 2, run 3, up 2 over 3, up 2 over, let's see, 1, 2, 3, 4, 5, there's 6. Okay, about there. Down 2, left 3 would be a good one to do. Try to hit those points. That's F. Okay, then over here, let's do the switcheroosies. So this is going to be x equals 2/3 y plus 2. Solving for y, I'm going to be subtracting 2 from both sides. Multiplying, or to get the y by itself, I have to, hopefully you remember this, you need to multiply by the reciprocal, 3/2. To both sides, since I'm multiplying that to the entire side, I need parentheses. So be careful there, make sure you get your parentheses in. And that's my f inverse, or y inverse. In order to graph that, I want it in slope-intercept form so that it's faster. So I'm going to distribute the 3/2. So I'm going to have 3/2 x, and then 3/2 times 2, or -2 in this case. These 2's are going to cancel when I multiply those together, so I'm going to get -3. Or you could think of it as multiplying the numerators and the denominators, you'd have -6 over 2, which is also 3. In this case, -3. Okay, there's f inverse. The work for that, if you need to see that, I could do it slow. It's 3/2 x minus 3/2 times 2. These 2's cancel. That's how I got the 3. Oh, what's a good color? I kind of like that tan color. So this one, the y-intercept is -3. 1, 2, 3. And I have a rise of 3, up 3, and then over 2. Up 1, 2, 3, and over 2. Let's do it one more time. Up 1, 2, 3, and over 1, 2. Whoa. That's f inverse. Go back to black. Put in the line y equals x as a visual check. It's going to basically run right through here at a 45-degree angle. And ideally, these are all going to cross. I just did it kind of sloppy. The idea is I could look at that and feel pretty comfortable that, yes, those are reflections over that line. So we have accomplished the goal on this one. which actually is going to bring us to our very last one. A clerk, now okay, this particular problem, notice, I mean obviously it's in the section where we're dealing with inverses. The book's intention is for you to use inverses to try to figure this out, but in my opinion, it's quite confusing to try to do it that way. So we're just going to go ahead and solve it and without worrying about inverses. And it is a pretty nice problem, so that's why I'm including it. So a clerk needs to price a digital camera that's been returned by a customer. The customer paid a total of $103.14, and that included a gift wrapping charge of $3 and an 8% sales tax. So now, what price should the clerk mark on the tag? Because they don't remember what the price of the item is, so they don't want to lose any money by mismarking it. So what we're going to do is we're going to, first of all, write an equation so we can get our mind wrapped around this. So they've got a total of 103.14. So let's start with that. Boring black again. I like blue. And okay, so that total of 103.14 is made up of the original price, which by the way, it says what price should the clerk mark? That's our X value, right? That's what we're trying to find. So this 103.14 included the price of the object, plus there was a gift wrapping charge of $3 added onto it. But there was also 8% sales tax charged. Now, did the customer have to pay the 8% sales tax on the $3 gift wrapping charge, do you think? And of course the IRS wants all their money, so yes. We have to, or the customer paid the 8% sales tax on this total X plus 3. So we want this X plus 3 to be in parentheses, because that's a total amount that we're paying a sales tax on. Okay, you could probably guess that the 8%, we're going to write it as a decimal of 0.08. If I just multiplied this all by 0.08, would I get a number? Well, would I get the right number? 0.08 times whatever that is not going to be the actual total price that was charged at the register. That's just going to tell you the tax. But the 103.14 includes everything. So what we have to do then is we have to multiply by 1.08, because the 1 accounts for the original price, in this case the price plus the 3, plus the 8% sales tax. So like the other day when we did the 1 plus or minus r, in this case it's 1 plus 0.08, or in this case 1.08. If you just multiply by 0.08 there, you're only going to be figuring out the tax, and this 103.14 is the tax plus the cost, the price, and the gift wrapping. So anyway, now we have this really nice formula, and now life is going to be much easier for us because we just need to find x. Now at this point you have a choice. You can solve for x right away, or you might want to distribute the 1.08 first. I personally would rather not do that. So I'll show you both ways. First I'm going to do it the faster way. I can divide both sides by 1.08, and the reason I can do that is because the 1.08 is being multiplied to this whole thing. So I need to get on my calculator now. 103.14 divided by 1.08 is 95.5 equals, that's gone, x plus 3. Subtract 3, and we can do that in our head. That's going to be 92.50. So that's the price the clerk needs to mark on the price tag. And then you could check it by saying, okay, that's the price on the price tag. We're going to add that $3 wrapping fee, so that's $95.50. And then we're going to figure out the tax by multiplying by 1.08. And I'm going to just double check, and sure enough, that's 103.14. If any of you have worked part-time in retail, you probably know about this, multiplying by the 1 point times the 1.0, whatever the tax rate is. Okay, so if you're happy with that, you can stop. I'm going to just keep going and just show you how to do it with distribution if you prefer. And then that will be the end of this. Okay, so if I distribute, this is different technique here. I'm going to have 1.08 times x plus 1.08 times 3, which is, we can actually do that in our head, because 3 times 1 is 3, and 3 times 8 is 24. And then we're going to subtract the $3.24 from both sides. That I'm not so hot at doing that in my head. I'm just going to do it real quick here on my calculator. Sorry, I'm not super fast at mental math. And then I just make a mistake if I try to do it, especially at the end of the day. So we get this, and then we're going to divide the 99.9 by 1.08. When I divide both sides by 1.08, I get 92.50. So I'm getting that same value. Okay, that's it.